Hi students, welcome to this part of the Capillary Electrophoresis instrumentation, and here we're going to speak about the detections method. There are a few very prominent detections you have to learn. One is the UV vis detector, followed by the indirect detection, fluorescent detection, mass spectrometry, contactless conductivity detection, the CCD. And as a reminder, for CE analysis, we are using very small samples. So how can we inject accurately and produce reproducible results, right, without causing dead volume here? And how are we able to use such a minute amount to measure with high sensitivity? All right. So UV vis absorption detector is one of the most widely available, and that's because for your sample, right, if you have a chromophore involved here, you can just detect it. And there's no need for derivatization. That means, right, you do not need to do an organic synthesis to tag a fluorescent dye for it to be detected. And it's also very simple because you can change the flow cell to change the pathway of the length of the light in the capillary scan. Now for indirect detection, the indirect absorption detection has been used for species with low molar absorptivity that are difficult to detect without derivatization. So the ionic chromophore is placed in the electrophoresis buffer, and then the detector receives a constant signal due to the presence of the substance. So indirect detections is about indirect absorbance detections that has been used for species with low molar absorptivity that are difficult to detect without derivatization. And ionic chromophore is placed in the electrophoresis buffer, and then the detector receives a constant signal due to the presence of this substance. And then analyte then displays some of these ions, just like the ion exchange chromatography, right? So that the detector signal decreases during the passage of the analyte band through the detector. Next, we have the laser-induced fluorescence detector, in short LIF, highly sensitive. And just like in HPLC, the fluorescence detection yield increases the sensitivity and selectivity for fluorescent analytes, or the fluorescent derivatives. So this LIF instruments, right, is preferred because it focuses the excitation radiations on the small capillary and to achieve a low detection limits available from intense sources. So most LIF attachments are available to couple with commercial C instruments. And they can detect as little as 10 zeptomoles or 6,000 molecules. For mass spec, very useful for structural determination and compounds identification. So this is also about structural elucidation. Whereas for others, right, it's a bit harder. You might have the same migration time and peak height, but you are not sure what identity of the compound is like. As we have learned in other spectroscopic and spectrometric techniques, spectrometry allows the fragmentation of the ions in a different way so that you can piece the puzzles together to identify what was the original species. And only volatile buffer should be used because we need to fragment the ions in a vacuum manner. But the demerit is high cost, very expensive method compared to the others. So this is a table that summarizes the detection modes of the CE and the limits there. As you can see, right, if we can push down the detection limit, it's better because it's more sensitive to measure a minute amount of the sample. So you can see why we prefer to use LIF. The laser-induced fluorescence is the best because it can measure very, very low, highly sensitive. But of course, the downside is the cost of repair is high, and the laser adapter, the module is not very cheap and affordable. Okay, so there might not be research group that can afford it. Now, let's talk a bit on the UV absorbance detection, right? So it really works on the Beer-Lambert's law that you have learned. Absorbance equals to the epsilon CL or ECL in short, right? So this is the constant molar absorptivity consistent for a molecule, right? And concentration, right? And the path length. So what you can see is, right, you measure the concentration based on the absorbance, but you can change the path length because the longer the path length, right, the higher the absorbance given the same molar extinction coefficient and the concentration, right? So if we want to have a high sensitivity, right, then we need to extend the path length. But how do we do it, right? How do we do it? later on we go through. There's a few methods. Now for UV, right, we need to make sure that we need to have a grading system. We can change the wavelength of the light we are trying to scan and detect our sample here. So if we have a unslitted light source, right, there's just white light, then it's not so accurate. So we like to apply the grading and inject a monochromatic light, that means of a single wavelength, as a standardized way to look at our species. So this is what it looks like here for a sample CE using UV detection. Here in this case, right, you see that if you change the monochromatic light from a 214 nanometer to 185 nanometer in terms of wavelength, you see a huge improvement. Why is that so? Number one is, right, the signal to noise ratio is better. Right, you see here the noises. In this case, the lower wavelength is better. And here you see this signal here is more accentuated, right? You can see. Although there's a flat path here, we just ignore it, but you look at the others, there's improvement. So for that, we need to do trial and error to see which wavelength is preferred for this sample. Next, we also consider another example here. Difference in the wavelength of the light in the UV absorbance detection, 200 nm to 280 nm. See a change, right? The improvement in the signal to noise ratio. Okay. So in this case, right, we are trying to look at the plot of the absorbance against concentration. Take note that the Beer-Lambert's law can deviate. There's always a limitation to that when if your detections is too concentrated. If your sample is too concentrated, then there's a deviation from Beer's law, which means it may not be a straight line. So there's always a linear range. Now, to have a larger linear range so that we can measure the concentration of a sample, we need to use a larger capillary. Here we see the difference in the capillary internal diameter. When we have a 75 nanometer internal diameter here, it provides a higher sensitivity. Okay, so the reason is, right, when you have a bigger volume internally here, there's a bit of excess the Joule heating. So with that, right, you have a peak broadening, which means there's some overlap. But what you want to is to resolve the peaks such that they are not overlapping. So you can see distinctively what the different peaks correspond to analytes there. And to do that, you can reduce the internal diameter to about 50 micrometer. As we have talked about in the last lecture, this is the commonly ID that we use for the capillary. Although it has a lower sensitivity, but you have a better resolution. Because the last thing we want is see electrophoregram is overlapping signals. Now we talk about to increase the absorbance, to increase the linear range, right? We can increase the path length. So one way to do it is we can either use a bubble cell, use a high sensitivity cell, or use a Z cell here, right? So how does it work? So for instance, right, a bubble cell is just in the middle. You have a wider kind of the diameter that's increased to 3 times the internal diameter. Z cell is like you have a little junction, so you extend it by applying this advantage of the horizontal length, right? Extend by 3 mm. High sensitivity detection cells, right, is a bit more mechanical, so this engineering you don't need to look at it so detailed, right? But it just increases the path length, 1.2 mm, okay, because it's a bit more packed. So for the capillary Z cell, to look at it closer, right, this is from Agilon, one of the manufacturer of CE, right, you see this extended pathway, this is what we improve on. So we'd like you to look at when we apply the capillary Z cell, right, how did the enhancement of the signal, right? So with a 3 mm Z cell, with just a 3 mm increment in the path length, the signals, right, in terms of the AU increase dramatically, right, compared to just an ordinary capillary. Look at that. Okay. Now next we go through the bubble cell. So take note that T1 and T2, right, is like, we look at T1 maybe a starting point, the sample is going to go in, and then at a certain time, right, T2, this is what happens. So let's focus, right, on bubble length, on sensitivity and resolution. At the start, when we have 2 sample zones, right, okay, and then when the first sample approaches this optical slit, okay, and exit here, this is what happens. This is without the bubble cell, okay. So you see 2 signals because this is the detection, right? You see, you only see one thing at a time, so there's no overlap. But when you have a bubble cell in this manner, when it goes in, sure, you have one signal, but there's a point where your first signal overlap with the sicker signal. Do you see here? You see that? That's why you see two peaks can overlap, which is something you want to avoid, right? And the reason for that is because the optical slit is too wide. That's why the peak merge. So to overcome it, it's a bit harder to change the bubble cell, but we can manage the slit width. So you see here with a lower, closer slit width, the same sample, right? At any point of time, there's only one signal. So you achieve both a higher sensitivity and higher resolution. Indirect UV detection, right? What happens is indirect means it's not measuring, okay, if there's something coming in, there's a peak. It's more of there's something coming in, there's lesser peak, right? Indirect, the opposite way, okay? Detect decreases in the background signal. So what happens is, right, this is the general scheme here. On the left, you have the mobile phase that contains all your buffer, your ordinary sample without your analyte here, right? So you scan, you have peak. But when you analyte, right, those in black, right, comes in, it blocks the detection. So you have a reduced detection, reduced absorbance, and therefore you have a drop in the signal, which means you have a negative peak. So in terms of this displacement, right, using the volume, right, this is what we call the TR. The transfer ratio is about to measure the number of molecules, background molecules, that's displaced, okay, by one analyte molecule. So in this case, we have something like cation displacement, right? So here your buffer cationic, but then here you have your analyte cations there. So you see that when you have your sample, then you see there's a drop in these two parts. Okay, so of course in your CE when you render your peaks, right? So I think they'll do an auto flip so that you see signals. There's a bit more common, right, upwards. Now, for indirect detections, right, there's a limit in the detections. The reason is quite simple. If you look at the previous slide here, if I block it, right, what you can measure is only 0, right? So, but it is not a reflection, true reflection of the highest concentration. I will use an analogy like stock market. You see, right, there's a lower limit how far I can go, which is 0, right? But there's no upper limit, right? If you can measure it higher, you know there's always room to grow to measure the absorbance of your analyte. But if you have a lower limit in this case, right, you can only say, okay, I block everything is 0. But what if there's a higher amount of your analyte within that space? Think a bit more. So here, okay. Anyway, we have a molecule called the limit detections. Concentration is calculated by these equations. So this Cm stands for the concentration of added background species, right? Either they are UV active, electroactive, or fluorescent. Dr is the dynamic reserve, the ratio of background signal to noise, right? And Tr is the number of background molecules displaced to replace by one analyte molecule, and we talked about in the previous slide the Tr, transfer ratio. It's preferred to have a smaller concentration limit of detection so that the C is more sensitive. And I'd like to conclude by saying that the indirect detection is most universal because you do not need any derivatization. So this example here, you have again your background electrolyte, absorbance, systems noise, due to components here, right, and your Dr is calculated in this manner. Next, we come to fluorescent detection. Just like UV, we need to find the optimum wavelength, right, for excitations that is give us the best signal to noise ratio. Now, anyhow, fluorescent detection, LIF, right, is very high sensitivity and specificity, right? Because to fluoresce, number one is already a first barrier. Not all molecule fluoresce. So there are some fluorescent dyes that is sold in the market. If we can do some tagging, do some covalent bond formation, so that the whole analyte, right, tag with fluorophore gets detected as a whole. Okay. This is a schematic diagram of LIF, laser-induced fluorescent. The light from a laser on the left, right, is focused first by the lens, so you don't have to waste so much energy. So you focus it, okay? And then this capillary with your electrolyte. Now the thing is, right, we do a right angle. We do a scan here, right angle, and we detect the using the photomultiplier in this manner. So the question is why we do not want to place it here just directly, because there might be noise due to the laser here, right? You have some scattering, right? You don't want to measure your noise. You want to measure what is absorbed and then emitted. Okay, very sensitive because it's about a monochromatic laser light, right? Which also means that the laser has to be very accurate, and when it's spoiled, it's not so affordable. Okay, the good thing about certain molecules is that it's a native fluorophore, which means that there's no need to do a synthesis, which means a lower yield, even contaminants, or even running a column. Can you imagine running a column on your mixture, right? And then after that, you have very low yield. We don't want that. So in this case, we are good that if, right, for a native fluorescent detection of tryptophan containing peptide, here I would like to focus. Here we have different conditions. What are they? You see for A, right? A is about using 200 nanometer. B is with xenon. Lamp excitation is 200 nm. So same wavelength but with xenon, inert gas. What happens there? Okay, you see for A, right, there are many signals, background signals. But for B now with xenon, I see only one signal. Okay, noise is reduced. And C, we have fluorescent detection with xenon and excitation of 280 nanometer. And this is what is best because we see one signal here, okay, of this species. That is our optimum excitation wavelength. Okay, the best signal to noise ratio. And to do that, we just have to try and error. That's about research, right? You explore the unknown, try, document it, and observe. These are some very important reagents. You need to know some of them. What does it react with, and I think these two are more important for you. At least you can name some of these species. APT is what we use in the lab a lot for carbohydrates. Excitation wavelength, emission wavelength. Yeah. Okay. So in this case, right, we are using argon ion laser, which is blue in color. Another example, this is another fluorophore dye scan, CBQCA here. Okay, your 3,4-carboxyl benzoyl 2-quinoline carboxyl aldehyde. Okay, you see how low we can detect 1.5 picogram, right? Very low and good detection limit. Only for CE. Okay, 442 nanometer. Yeah. Alright, I'll continue the next part later.